All right, so hi everybody, welcome back. Today we're going to be finishing up our chapter 33 lecture on optical instruments. So by the end of this video, we'll be done with everything from chapter 33. And the next topic that I want to get into is cameras in the human eye. So what we're going to do here is take what we've learned about lenses and apply it to understand how cameras in the human eye work. Okay, so let's start with digital cameras. Now, a digital camera can be something like a standalone digital camera like this one shown in the diagram, or a digital camera attached to your phone or your computer. These all kind of work in the same way. So let's talk about some of the components of a digital camera. So first, we have an aperture. So an aperture is an opening in the camera whose size can be adjusted to change the amount of light that's coming in. So this is the aperture. We can close it up to make it smaller. We can open it up to make it bigger and have more light come in. That's what adjusts the amount of light coming into the camera. Okay, of course we have a lens to focus the light that's coming in. And then behind that lens, we have something called a charge-coupled device, or a CCD. So this is basically a sensor that measures light intensity at each location. So the CCD is made of many little pixels, and at each pixel, it can measure the intensity of the light that's hitting that pixel. Now, in earlier cameras, before we had digital cameras, we would use a roll of film in place of the CCD, but it would basically do the same thing. It would measure how intense the light is at each location. Now, in order for this to work, in order for us to capture an image using a digital camera, the image must be formed on the CCD. In other words, we have rays of light coming in, going through a lens. They must focus, they must converge on the CCD in order for us to capture an image that's in focus. If the image is not forming on the CCD, then it's going to look blurry. Okay? So in order to make sure the image is in focus, we'll have to adjust things. So the lens of the camera can be moved away from the CCD in this direction or towards the CCD in this direction to make sure that we always get an in-focus image forming on the CCD. Now let's talk a little bit about how that CCD works. So again, a CCD is just a big array of many pixels. On modern cameras, you might have several million pixels on your CCD. And for each pixel, if a particle of light, which we call a photon, hits the CCD, then electrons will be knocked into the potential well of that CCD. So in other words, a light particle comes in, it knocks electrons into a place where they can be stored in the pixel of the CCD. Now, basically, the more light particles that are coming in, the more electrons that we end up accumulating. So we can measure the intensity of the light by just counting how many electrons we accumulated in each pixel of the CCD. Okay, so when we expose the picture, we basically have a bunch of electrons being stored in all of these different pixels. But then we have to read them out. Okay, we have to take those electrons and move them somewhere where we can read out their values. Okay, and so how do we actually do that? Well, this animation will show us. So this is a CCD with a bunch of different pixels, and at each pixel, if light comes in and hits the pixel, that knocks electrons into a potential well where they can be stored. So basically each pixel has some number of electrons being stored there, and the more light that hits the pixel, the more electrons we'll have. But if we actually want to read out those values and save this image to a file, we're going to have to move these electrons somewhere else where they can be read out. So here's how that works. First, we're going to move each of these rows of pixels down into this region, which is called the readout strip. Okay? Then once they're moved here, they're going to be moved to the right into what's called the output amplifier. And that's what actually reads out the number of electrons in each pixel. So we have to take each pixel one by one and read out how many electrons are stored there. So this is how that will go. So again, first we move a row of pixels down into the readout strip, and then we move each one to the right into this output amplifier where we can actually count how many electrons are there. Okay, so there's one other element to this, which is color. So just by counting how many electrons we have in a pixel, all we're doing is saying what the intensity of the light is hitting each pixel. That doesn't tell us anything about color. So if we want to detect color, we're going to have to do something extra. So here's one way you can capture a color image. There's more than one way to do this, but a simple way to do it is to put on top of your CCD an array of filters. So we have green filters, red filters, and blue filters, okay? And they're arranged in this kind of tile pattern over the CCD. So think about this. If you have a pixel with a blue filter on top of it, that's only letting blue light go through. So this pixel is not only telling you how intense the light is, but it's telling you how intense the blue light is. And similarly, if you have, let's say, a red filter on top of your pixel, that will tell you how intense the red light is. So now you can get information about color in your image. And so a digital image is just a huge list of intensity values for each pixel. It's just a list telling me at this pixel how intense is the light. And then if it's a color image, it will tell me how intense is the light of each color, red, green, and blue. So when you take a picture of something using your phone, and then that file gets saved to your phone, that file is just a huge list of intensity values for each one of those pixels in your phone's camera. So this is a nice analogy that helps us understand how a CCD readout works. So we're going to imagine that we have a two-dimensional grid of buckets. So each one of these is a bucket, and these buckets are on conveyor belts. So let's imagine it's also raining, so that each bucket is collecting water. So in this analogy, each bucket is like a pixel in our CCD because it's telling us how much water is accumulating at each point, just like a pixel is telling us how much light is hitting each point on the CCD. So it rains for a while and we collect water for a while, but then we want to actually measure how much water accumulated in each bucket. So what we're going to have to do is move each one of these buckets somewhere where we can measure the water level. So that's where the conveyor belts come in. So we're going to move each bucket onto this conveyor belt, and then this conveyor belt is going to move them into what we call the output amplifier. So in this analogy, imagine this is something that can actually measure the water level in each bucket. In the CCD, this is what would tell us how many electrons are in each pixel, okay? So if we read this out, we can get a sense of the intensity that was measured in each pixel. And so if we're using buckets and conveyor belts like this, of course, it would be a very slow process to read out how much water is in each bucket. But think about what's actually happening in the CCD of, let's say, your phone's camera when you capture a video. So the CCD is going to have several million pixels. And if you're taking a video, typically that's going to be at 30 frames per second or so. And that means every single second, you're capturing 30 different pictures, 30 different images from your phone's camera. So in the span of 1 second, what's happening is light is coming in, hitting each pixel. Then the electrons stored in each pixel are moved somewhere where they can be counted and then stored. That data can be stored. And then that whole process repeats 30 times. Okay, so next, let's talk about the human eye. And in a lot of ways, the human eye is pretty similar to a camera because you have light coming in and then going through a lens, and that lens focuses the light somewhere where it can be detected. So there's some kind of detector back here, much like the CCD of a camera, that actually measures the intensity of the light at each position. Of course, the details are very different, so let's talk about some of the components of the human eye. So here we have a diagram which points out some of the different parts of the human eye, and let's just discuss what some of these components actually do, what function they serve. So we'll start with the iris. So the iris is a muscle in your eye that adjusts the aperture. Remember, aperture is the opening where the light is coming in. So for the eye, this aperture would be called the pupil. That's the opening where the light comes in. And as you know, the size of your pupil can be adjusted. It can get bigger to let more light come in when it's dark, and it can get smaller for less light to come in if it's very bright. All right, so next we have the ciliary muscles, which adjust the shape of your eye's lens. So in a camera, we can simply move the lens in and out in order to adjust the focus, so we can see things in focus that are really close to the camera, and we can see things in focus that are really far away from the camera. For your eye, that's not really going to be possible. Your lens is pretty much in a fixed position. But what we can do is change the shape of the lens. And when we change the shape of the lens, what we do is we change F, we change its focal length. So your ciliary muscles just pull on the lens to stretch it out. And if they relax, then it puts it back to its original shape. That's the idea. So you might notice when you read and you're holding a book up close to you for a very long time, it can sometimes hurt your eyes. It can strain your eyes. That's because your ciliary muscles are working really hard to stretch the lens of your eye out in order to focus the light that's really close. On the other hand, if you're looking at things that are far away, these muscles relax, and so it puts less of a strain on your eye. So if you've ever had your eyes strained by looking at things that are really close, like a book or a computer screen, it's probably because of this. You're working your ciliary muscles way too hard. Okay, so next we have the retina, which is in the back of the eye. And basically, this contains the eye's photoreceptors. And that's just a fancy way of saying the things that detect light in your eye. We call these the rods and the cones. So the cones are responsible for detecting color. So the whole reason you can see in color is because your eye has cones. And they also are responsible for detecting things with high spatial resolution. So when you see things in a lot of detail, your cones are responsible for that. So the cones tend to be kind of concentrated mostly in the very center of the retina, which is what we call the fovea. The rods, which don't detect color, are more spread out throughout your entire retina. And then finally, we have the optic nerve. So the optic nerve is responsible for sending electrical signals from your retina, which is detecting the light, to your brain. So your brain can actually process that information. Okay, so next, let's talk about corrective lenses. Things like glasses and contact lenses. Many of you out there probably wear corrective lenses of some type. So let's talk about why that's even necessary in the first place. So the basic idea is that an image formed by the lens of your eye has to form on the retina in order for you to see it in focus. So rays of light come into your eye. The lens of your eye is actually a converging lens, so it makes those rays come together. And the point where those rays of light come together should be exactly your retina in order for you to see a sharp image that's in focus. If these rays are not coming together on your retina, then it looks blurry, okay? So if you don't need corrective lenses, then your eye is capable of focusing light from a really large range of distances. So a normal eye, one that doesn't need corrective lenses, is capable of focusing light from objects with a distance DO as small as 25 centimeters, and then out all the way to infinity. Okay, so these are what we call, by the way, the near point and the far point of your eye. The near point is the closest distance that your eye can focus on, and the far point is the largest distance, the furthest distance that your eye can focus on. So for a normal eye, the near point, N, is 25 centimeters. You should be able to focus on things as close as 25 centimeters. And the far point is infinity, meaning there's no real limit to how far away an object can be so that you can focus on it. Okay? If your eye is farsighted, on the other hand, that means your eye can't actually focus light from objects that are close by. In other words, the near point is greater than 25 centimeters if you have a farsighted eye. So to correct for that, you need a converging lens. So here's what's going on. Light rays come into your eye from a close by object, and when your lens focuses those rays, they're supposed to converge on the retina, but they don't. Okay, they actually converge at a point that would be further away than your retina. So if you get a converging lens and put that in front of your eye, well then it will help those rays come together more easily. So now the rays of light come in, go through the corrective lens, and then go through the lens of your eye. And so now those rays are focusing on the retina, and you can actually see that close by object. On the other hand, if you have a nearsighted eye, that means you can't focus light from distant objects. So your far point should be infinity, but it's less than that if you have a nearsighted eye. So to correct for this, we use a diverging lens. Okay, so here is your eye without any corrective lens. We have rays of light coming in from a distant object, let's say it's infinitely far away, and those rays go through the lens of your eye, but those rays actually focus at a point that is too close. So they should be focusing over here at your retina, but instead they're focusing closer to your lens than that over here somewhere. So what we need is for those rays of light to diverge a little bit. So if we put a diverging lens here, the rays of light go through that and then go through the lens of your eye, and now they're focusing at the right point, which is your retina. Okay? So that's the idea behind different types of corrective lenses. Okay, so that takes us to angular magnification. Now, the thing to realize here is that when we look at an object, how big it appears to be doesn't actually depend on the size of the object. It instead depends on the angle that that object takes up in our field of view. In other words, it's the angle subtended by an object that determines how large it looks in your field of view. So let's take a look at an example here. We have two objects, A and B, and object A is the same size as object B in the sense that if we were to measure the height of each one in meters, we'd get the same answer. But object A is closer than object B. So even though they have equal size, it's going to seem to us like object A is bigger when we look at it because it takes up a bigger angle, it subtends a bigger angle in our field of view. So object A subtends an angle theta 2 here. Object B subtends this angle theta 1. And again, it's that angle that determines how large the object appears to us in our field of view. So even though these objects have the same size, they seem like they have different sizes because we're viewing them at two different distances. Okay? So given that it's the angle that matters as far as how large something looks in your field of view, we'll define something called the angular magnification. So angular magnification is given by capital M, and it's the ratio of the angle subtended by an image on your eye when you have the aid of an optical instrument. So we'll call that theta prime. That's the angle that it takes up when you have an optical instrument helping you out. And then when you don't have an optical instrument helping you out, the angle is theta. Okay, so the ratio of those two is theta prime divided by theta, and that's what we call the angular magnification of that instrument. So it's not about how the size changes, it's about how the angle changes when you have an optical instrument. That's the angular magnification, and that's what's actually relevant to us when we're trying to make things look bigger in our field of view. Okay, So next, let's consider a simple magnifier. So here I'm thinking about something like a magnifying glass that you would use to read really small text or to see the fine details of things that you wouldn't otherwise be able to see. Now first, let's think about what happens when it's just your eye looking at an object without the aid of a lens. Okay, so it's just this object in your eye, that's it. So in this case, the largest angle that you could see with the eyes still in focus would be when you place the object at the near point of the eye. Remember, the near point is the closest distance that your eye is capable of focusing on. So you couldn't put the object any closer than that because then it would start to appear blurry. So the near point for most people is about 25 centimeters, by the way. So we have an object, the height of it is HO, and then we have the distance between that object and your eye is N, the near point, okay? So let's consider a ray of light coming from the top of the object into your eye. That's gonna make an angle which we'll call theta with respect to this line at the bottom of the object. So in other words, that's the size of the object in our field of view, theta. Now, as long as we assume small angles, which is what we'll do throughout this, then theta is approximately equal to h0 divided by n. So the idea behind this is, as long as the angle is small, we can approximate h0 as a tiny little arc along a circle where the radius of that circle is n. And remember, the angle inside of a circle is equal to the arc length, which in this case is h0 divided by n, which is the radius. So again, this is valid, assuming we have small angles. Okay, so now let's see what happens when we add a lens to this picture. So specifically, this will be a converging lens. Now, we can put the lens any distance away from the object that we want. So for now, let's take the object to be at the focal point of our lens. So in other words, the distance DO between the lens and our object is the same as the focal length F. Okay, and with that said, let's get a sense of how this lens is forming an image by drawing a ray diagram. So one principal ray goes parallel to the optical axis and then out through the focal point after going through the lens. Another ray we could draw goes straight through the center of the lens without being bent. So these are the rays that are entering your eye, okay? Now, if we trace those rays back behind the lens, like this, it looks like they're coming from infinity. It looks like they're coming from something that's infinitely far away because these lines are parallel. You'd have to go an infinite distance in this direction if you ever wanted to see them converge. So effectively, it's like you're focusing on something that's infinitely far away. And that's why this is helpful, because instead of straining your eyes and trying to focus on something that's really close, you're actually focusing on something that's infinitely far away. So what's the angle then that image is going to take up in your field of view? Well, it's this angle in our diagram right here, theta prime. So with the aid of the lens, and again, we're assuming small angles here, theta prime is going to be h0 over f. Again, consider this to be an arc length divided by a radius, which is valid if we're using the small angle approximation. Okay, so we have both theta, which is the angle without the aid of the lens, and then theta prime, which is the angle with the aid of the lens. Now the angular magnification is defined as theta prime over theta. So this divided by this will give us n divided by f. So it's your near point divided by the focal length of the lens. That's the angular magnification you're going to get if your eye is focused at infinity, as we said earlier. Okay, so of course we don't have to place the object right at the focal point of the lens. We can put it anywhere, and depending on where you put the object relative to the lens, you'll get different amounts of angular magnification. So now let's consider the case where the image forms at the near point of your eye. So in other words, we want the image formed by this lens to be at the near point of your eye. In order for that to happen, we must place the object inside of the focal length of the lens. So here's what we have. Object, the height of it is HO, the distance from the lens is DO, and to see where the image is forming, we can draw a ray diagram. We have one ray of light coming from the tip of the arrow, going parallel to the optical axis, and then out through the focal point over here. Again, another ray that we could draw goes straight through the center of the lens without bending. So if we trace those rays back behind the lens, these are what we call the virtual rays, then we'll see that they converge over here, and that's where the virtual image is forming. Now remember, in this case, we want the image to be forming at the near point of the eye. So that means DI is equal to the near point. The image distance is equal to the near point, in other words, but we put a negative sign in front of that because it's a virtual image. So it carries a negative sign. Okay, now the angle that is subtended by this virtual image is going to be theta prime. So this tells you how big that image is going to look in your field of view. But as before, theta, which is the angle without the lens, just with the naked eye, is equal to h0 divided by n. So if we want to know the angle subtended by this virtual image that the lens forms, that's theta prime, according to the diagram, that's just HO divided by DO, again, assuming small angles. So if we want to know the angular magnification then, provided by this lens, that's theta prime, what we get when we have the lens, divided by theta, which is without the lens. So we're taking HO over DO and dividing HO over N. So HO will cancel out and we'll only be left with N divided by DO. So if we could find a formula for DO, the object distance, then we could figure out what the angular magnification M is. So for that, we're going to apply the thin lens equation. Remember, 1 over DO plus 1 over DI is equal to 1 over F. So if we just take 1 over DI to the other side, we'll have 1 over DO equals 1 over F minus 1 over DI. So let's just replace that in our equation for the angular magnification, where we have 1 over DO. We're going to replace that with 1 over F minus 1 over DI. And that's what's multiplying N out here. But then remember that DI is just equal to minus N. So we'll replace DI with minus N right here. So what we get is the angular magnification M equals N times 1 over F plus 1 over N. And that can be simplified because if we distribute the N into the parentheses, we get N divided by F plus 1. So here, your eye is focused at the near point because that's where the image is forming. Okay, so that's what you're looking at, is something that's at the near point. And with that, the angular magnification you get is N divided by F plus 1. So it's an even bigger magnification than before when you're focused at infinity. So let's do an example with that. Suppose you have a magnifying glass, which is just a converging lens with a focal length of 8 centimeters. So what angular magnification can you achieve with your eye focused at infinity? And then as a follow-up, what angular magnification can you achieve with your eye focused at the near point? So this would be the best possible angular magnification. Let's take the near point of your eye to be 24 centimeters in this calculation. Okay, so just use the two formulas we derived and pause the video for a second, see what you get, and then come back to it. Okay, so remember, with the eye focused at infinity, the angular magnification, capital M, is given by N divided by F. So the near point of your eye divided by the focal length of the lens that you're using. So this would be 24 centimeters over 8 centimeters. So 3 times. So the object you're looking at will be 3 times as large if you use this magnifying glass. On the other hand, if the eye is focused at the near point, then you get an even larger magnification, which is n divided by f plus 1, which would be 24 centimeters over 8 centimeters plus 1. So 3 plus 1 is equal to 4. Now you get 4 times magnification if you have your eye focused at the near point. Okay, so pretty simple. Okay, so next, let's take what we've learned so far about lenses and mirrors and apply that knowledge to understand how a telescope works. So it turns out there are many different types of telescopes, different designs, and broadly speaking, we can classify telescopes as either refracting, which means the telescope is made out of different lenses, or reflecting, meaning the telescope is made out of mirrors. So one specific type of refracting telescope is called a Keplerian refracting telescope, and it just has 2 converging lenses. So it's a pretty simple design. You just have 2 converging lenses. Now, one of those lenses is called the objective lens, and this one is generally going to be larger. And then you'll have a smaller lens called the eyepiece. Okay? And basically, we're using these lenses to focus light from very distant objects. Since we're looking at things like stars and planets, we can essentially assume that the distance is infinity for those objects. Okay, so now let's consider rays of light coming in from an object that's infinitely far away. So specifically, this ray is coming from the top of our object. So imagine there's an arrow infinitely far away from the lens, and this ray is coming from the top of that arrow. So this one will go through the focal point of our objective lens, and then it will go out parallel to the optical axis. If we draw another ray of light, again, one of the principal rays we could draw comes from the object, and then it goes straight through the center of our objective lens without being bent. So where does the image form from the objective lens? Well, it forms right here where those 2 rays converge. And let's take note of the fact that the angle subtended by our object, theta, is shown right here. So it's the angle between our optical axis and these incoming rays. Okay? So let's show what we call the intermediate image. This would be the image formed by the first lens, by the objective lens. This is a real image, but it's inverted. It's upside down. And where does it form? Right at the objective lens's focal point. Okay, so next, we'll see what happens when the light goes through the eyepiece. So it's going through another lens. And what we're doing here is just drawing 2 of the principal rays. So one of them goes through the center of the lens without being bent, like this. And another one we could draw goes parallel to the optical axis and then comes out going through the focus. So these would be the rays that you actually see, because you look through the eyepiece when you observe something through a telescope. So these are the rays that you would actually see. Now, if you trace those rays back behind the lens, they're actually just parallel, so they don't ever converge. The final virtual image is forming at infinity. Okay? So if we think about what angle that final image subtends, that would be theta prime, shown right here. Okay? So theta is the angular size without the telescope, and theta prime is the angular size with the telescope. So with the telescope, we get a bigger angular size. The angular magnification is going to be given by capital M equals theta prime divided by theta. So using this diagram, we're going to work out what the formula for this magnification is. Okay, So if we're going to work out what the angular magnification is, I just want to point out that there is a triangle in this diagram that we're going to focus on for now. This one right here. And the angle inside that triangle is theta, the same as this angle theta out here. So let's copy that triangle down. Angle theta, right angle here. And the horizontal side length is FO, the focal length of the objective lens. The vertical side, let's call it H. That's just whatever the height of this intermediate image is. There's another triangle I want to point out here, which I'll show with a different color. This one. And notice how we have the angle theta prime inside of that triangle. So if we copy that one down, we have the same side length H going vertically here, a right angle here, and then the horizontal side is FE, the focal length of the eyepiece. So that angle is theta prime. Okay, so let's come up with formulas for theta and theta prime. Now, since we're dealing with small angles, okay, we're making an approximation. Tangent theta, by definition, is sine theta over cosine theta. But when we have small angles, sine theta is approximately equal to just theta, and cosine theta is approximately just equal to 1. So in other words, the angle that we're looking for is approximately equal to tangent theta as long as the angles are relatively small. So remember that tangent is just opposite over adjacent. So in other words, the angle itself that we're looking for is approximately equal to the opposite side over the adjacent side in the triangle we drew. So for the first triangle, the opposite side is H, and the adjacent side is FO. For the second one, where the angle is now theta prime, the opposite side is H, and the adjacent side is FE. So that's approximately what those two angles are equal to. Now, the angular magnification M is just theta prime over theta. So what we have is H over FE divided by H over FO. Cancel out H, just gives us FO over FE. So here's the idea behind this type of telescope. You want an eyepiece with a very small value of the focal length, and you want an objective lens with a very large focal length, okay? And the bigger you can make that ratio, the more magnification you can get. Okay, so the result we get is that the angular magnification is the ratio of FO divided by FE, just the two focal lengths for your objective and your eyepiece. We put a negative sign here in the final answer, by the way, because the final image is inverted. Remember, we were tracing rays from an object that was up here somewhere, but then the final image ended up being down here, so it's inverted. When you use this type of refracting telescope with just an objective lens and an eyepiece, everything is going to look upside down when you look through it. Okay, so if we want to build the best possible, the most powerful refracting telescope that we can, the idea is to get the best angular magnification, we want a very large value of FO and a comparatively small value of FE. So we want the largest possible focal length for the objective lens. That's how we get the best magnification. Now, in this design, those two focal points for the objective lens and the eyepiece actually coincide with each other. So this means the bigger the angular magnification, the longer the telescope is going to have to be, okay? Now, you can only build a telescope so long, so that's really what's going to limit how much magnification you get out of a telescope like this. So the world's largest refracting telescope that exists is found at the Yerkes Observatory in Williams Bay, Wisconsin. And this telescope has an objective lens with a focal length of 19 meters and an eyepiece with a focal length of 10 centimeters. So we can easily calculate the magnification we get. 19 meters FO divided by 0.1 meters for FE is 190. So this gives you 190 times magnification. But in order to actually build this thing, it needs to be housed inside of a tube that's about 19 meters long. So over 60 feet long. It's a very large telescope. And keep in mind, you're going to have to be able to move the telescope around because you want to point at different things and keep track of different objects in the sky. So this is a very difficult thing to do. You need to build this absolutely gigantic piece of machinery that you can move around and point in different directions. So this is the largest one that was ever built. Now, if you take a look at the picture of it, it actually looks very old. So why is it that the largest refracting telescope in the world is so old? Haven't we built new ones since then? Well, the reason we haven't done that is that refracting telescopes that use lenses are kind of obsolete. They're not really used anymore. And the reason, or at least part of the reason for that, is something called the chromatic aberration. So the index of refraction of glass, N, is not just a constant. It slightly depends on the wavelength of the light that's going into the lens. So the N value for red light traveling through glass is slightly less than the N value for blue light traveling through glass. And the result of that is what we call the chromatic aberration. Light rays with different colors, after they go through the lens, are going to focus at different points because they get bent a different amount by the lens. So your red light is going to focus over here, whereas green light is going to focus over here, and blue light will focus over here. That's not what we want. We want all the light to just focus at a single point so we get a very sharp image. But again, instead, what you get is different colors focusing at different points. So here's an example of that. This is an image of the planet Jupiter that's captured with a small refracting telescope, and you can see this chromatic aberration. In other words, the red and the blue light is not focusing at the same point, and that results in a blurry image, okay? So to get around that, we use reflecting telescopes. The nice thing about reflection is that the law of reflection, which says the angle of incidence equals the angle of reflection, that doesn't depend on the wavelength of the light. It's just theta I equals theta R regardless of the wavelength of your light. So we don't get this chromatic aberration when we have a reflecting telescope, one that's based off of mirrors as opposed to lenses. So here's one very simple design for a reflecting telescope. It's called a Cassegrain reflecting telescope. Here we have a very large primary mirror, which has a concave shape, and then a smaller secondary mirror, which has a convex shape. All right, so here is our primary mirror. It's the much larger one with the concave shape. There's actually a small opening at the very center of that mirror. Here's our secondary mirror, and this is the one with the convex shape that's comparatively much smaller. So if we consider what happens when we have rays of light coming in from a very distant object, again, essentially the object distance can be treated as infinity. Let's see what happens to those rays of light. So here's one ray, comes in, it reflects off the primary mirror. Angle of incidence equals angle of reflection. So the reflected ray goes this way. It reflects off the secondary mirror. Again, angle of incidence equals angle of reflection. So that ray that reflects off the secondary mirror ends up going in this direction. If we look at another ray of light coming in from down here, it bounces off the primary mirror, then off the secondary mirror, and then it goes out this way. So these rays of light coming off the secondary mirror go through the opening in the primary mirror. And at some point, they're going to converge. So this is where an image is being formed by our telescope, where those different rays of light converge. Now, ideally, this is where you would put an eyepiece if you wanted to actually look through the telescope and see the image that it's forming. Or you could actually put a camera there to capture the image that's being formed by your telescope. So you could put like a CCD here and capture the image. So we're not going to derive this formula for the angular magnification. I'm just going to tell you what it is. The derivation is actually very similar to what we did for the refracting telescope. The angular magnification is given by m equals minus fp over fs. So fp is the focal length of the primary mirror. Fs is the focal length of the secondary mirror. So again, it's just the ratio of two focal lengths that gives you the magnification. So with that said, let's do an example. Suppose you have a reflecting telescope that has a primary mirror with the focal length of 45 centimeters and a secondary mirror with a focal length of 15 centimeters. So let's say we're looking at the moon through this telescope. Without the aid of a telescope, okay, if you're just looking at the moon with the naked eye, it takes up about half a degree in your field of view. So the question is, if you're now looking at the moon through this telescope, what is the angle that it subtends in your field of view? So to do this, you're going to be using, of course, the formula for angular magnification of a reflecting telescope. So pause the video for a second, see if you can work this out, and then we'll go through it together. Okay, so this is a pretty simple calculation to do. First, let's remember that the definition of angular magnification, so we show a definition with this symbol, that's theta prime over theta. But in the case of a reflecting telescope, this would be minus fp over fs. So theta prime, which is the angle we're looking for, that's how large the moon appears in our field of view when we're looking through this telescope, that would be minus fp over fs times theta. Okay, so now we can just directly calculate this. We have minus. The primary mirror has a focal length of 45 centimeters. The secondary, 1.5 centimeters. And then theta, this is how big the moon appears in your field of view without the aid of a telescope. So just with the naked eye, this is 0.5 degrees. Now, if you do this calculation, you're going to get minus 15 degrees. So this is the angle subtended by the moon when you look through the telescope. So it looks much bigger. That's what you want the telescope to do. Okay, and then the negative sign indicates that the image you see is inverted. Okay? So that's how this works. So I thought we would spend the rest of the time here in this video talking about modern telescopes. So what are some of the more recent developments that have been made to improve telescope technology over the last couple decades? So the first thing to note is that almost every modern telescope that's used for scientific research is a reflecting telescope. Because if you remember, refracting telescopes that are made out of lenses suffer from chromatic aberration. And that means the images produced are much more blurry than they should be. When you have a reflecting telescope, you don't have that problem. So these are much more suitable for scientific research. So here are a few different things that have developed over the last couple decades to improve our technology and make our telescopes more powerful. So the first thing is very simple. If you want a more powerful telescope, you need to build a larger telescope. When you increase the size of the primary mirror, you improve the magnification you get. You get a bigger magnification than before, which means you can see the more fine details of things. You increase your spatial resolution, in other words. And not only that, since you have a bigger mirror, you can collect more light. So you can see fainter objects than before. You can detect things that were too dim to see with smaller telescopes. So an easy improvement to make is just to build bigger and bigger telescopes, and that has been the progression of things over the last several decades, just building bigger telescopes. So another really important development in the last couple decades is that a lot of the work that's done in operating a telescope, collecting data from a telescope, and analyzing data from a telescope is now automated by computers. So work that used to be done by people can now just be done automatically by computer systems. So there are several different robotic telescopes out there that are just collecting data all on their own, and that data gets fed into AI systems to analyze. And the overall effect of that is that you can study a much larger amount of data, a much larger volume of data can be studied compared to just having people do this work by hand. Another interesting development is that we can now correct for atmospheric blurring. So you may have noticed, if you've ever looked into the sky at night, you can see stars sort of twinkle. Now, that is an effect of the atmosphere. The fact that when we look into space, we're looking through Earth's atmosphere, that has an effect on the light that comes in. In other words, the atmosphere tends to blur the light. So we can correct for that with what's called an adaptive optics or AO system. So let me just show you an example of an image taken of two stars without adaptive optics, which looks like a complete mess. It's just a blur of light. You can't even make out each individual star, and that's because of the effect of the atmosphere in distorting the light that's coming in. With adaptive optics, when we correct for that, now you can very, very clearly see that there are just two separate stars there. So the way this works is pretty amazing. So you have some light coming in. This is a wavefront that's coming in, and it's being distorted by the atmosphere. And then here we have a mirror, which is actually deformable. So you can change the position of each part of the mirror with a little motor which pushes on it from this end. So in other words, if the atmosphere distorts our wavefront, we can correct for it by distorting the mirror that it hits, and then what reflects off of that mirror is a corrected wavefront without that distorting effect. So what really makes adaptive optics so amazing is how fast these systems can operate. So every single second, here's what happens. You have a measurement of the distortion that the atmosphere is introducing. Then you send that to a computer. You have it calculate how this deformable mirror needs to move in order to correct for that. Then it puts the mirror in the correct position. And then, of course, you get a corrected wavefront once the light reflects off that mirror. But that whole process happens 1,000 times every second. So every single second, there are 1,000 corrections being introduced to account for the blurring effect of the atmosphere. Now, one very simple way to get rid of the effect of Earth's atmosphere when you're observing things with the telescope is just to put the telescope in space. So that way, when you observe something, you don't need to look through Earth's atmosphere, and you don't have to worry about the blurring effect that will introduce. So now we have a whole bunch of different space-based telescopes that are in operation. The most famous one is probably the Hubble Space Telescope, or HST. So Hubble is in low Earth orbit. It's orbiting the Earth at about a height of 540 kilometers. And it's been in operation for a very long time. It was first launched in 1990. And the design of the telescope is Cassegrain. So this means we have a primary mirror and a secondary mirror. For Hubble, the primary mirror is 8 feet in diameter. That's about 2.4 meters. And there are a whole bunch of different instruments on board the Hubble Space Telescope that allow it to take images of things and to perform spectroscopy. This means we can see the spectrum of the light that's being emitted by an object. An interesting fact about Hubble is that when it was originally launched, it was found that the primary mirror was polished into the wrong shape. So there was a mistake made in actually shaping the primary mirror. And you can see the effect of that in some of the early images that were taken by Hubble. It was kind of a disaster, actually. The fact that, all this money and time and energy was put into this telescope, and then when it first takes an image, it's really not that good. Okay? Fortunately, this defect in the mirror was corrected in 1993 by introducing some new instruments to correct for the effect. And after that, things are looking a lot better. So Hubble now is still one of the best telescopes we have in terms of observing the fine details of stars and galaxies out there in the universe. So these days, we also have some very impressive ground-based telescopes. So in particular, let's take a look at the Keck Telescopes. These are 2 telescopes nearly identical to each other that are located at the summit of Mauna Kea in Hawaii. So Mauna Kea is the tallest mountain on the big island of Hawaii. That's where these telescopes are located. And these telescopes are absolutely gigantic. The primary mirror of each one is 10 meters in diameter, which is about 33 feet. And it doesn't consist of just a single piece. Instead, the primary mirror consists of 36 different hexagonal segments that are arranged together to form the primary mirror. So it has a structure that looks kind of like a honeycomb if you look at it. The primary mirror is actually so big that it can deform under its own weight. So that's a problem that needs to be corrected for. So there's a computer-controlled system of sensors and motors on board the telescope that detects when a mirror is going out of alignment, and then the motor adjusts the position to correct for that. So it's constantly correcting for the shape of the mirror as the telescope moves around to ensure that the shape doesn't change, because that's very important, that the mirror maintains a certain shape in order to collect light in the proper way. So we've seen what the state of the art looks like for current telescope technology, but what will things look like in the future? What is the next generation of telescopes going to be like? Well, the first thing is the James Webb Space Telescope. This is expected to be launched in 2021. We'll see if that actually happens. It usually gets moved back from the expected launch date. So in the next couple years, we expect that the James Webb Space Telescope will be launched. And this is going to be the successor to the Hubble Space Telescope. So the Hubble Space Telescope is already quite old, so it's time for something new to replace it, something that's more powerful, and that will be the James Webb Space Telescope. So the primary mirror of the James Webb Space Telescope is going to be 6.5 meters in diameter, so much larger than Hubble. And it's so big that we can't make it out of a single segment. It's going to consist of 18 hexagonal segments arranged in the honeycomb structure we saw before, like this. And then later in the decade, around 2027, it's expected that the 30-meter telescope will be completed. This is a telescope that's currently under development, which, when it's constructed, will consist of 492 hexagonal segments. Absolutely gigantic telescope. The primary mirror is 30 meters in diameter, about 100 feet, and this will be by far the largest telescope ever constructed once it's built. And it will be far more powerful than any ground-based telescope like the Keck telescopes. So it'll be really exciting to see what we can learn about the universe with this next generation of more powerful telescopes that is coming out. Okay, so I thought we'd end things here by telling you a little bit about the research I did while I was a PhD student at UC Irvine. So I studied at UC Irvine from 2010 to 2016, and from about 2011 to 2016, I was involved in a research project. So as part of this research project, I collected data from the Hubble Space Telescope and from the Keck Telescope. So I've actually worked with these instruments in my research. And what I was studying are these objects called nuclear star clusters. So nuclear star clusters are really dense collections of stars that are located at the centers of galaxies. These are really common objects. About 60% of elliptical galaxies have a nuclear star cluster at the center, and about 75% of spiral galaxies have a nuclear star cluster at their center. The Milky Way galaxy, the galaxy we live in, has a nuclear star cluster at its center. So these are very common objects. And my project was basically to study what their properties are. And so these objects are really densely packed with stars. When we talk about a stellar density, we mean how many stars are there per unit of volume in a given region of space. So if we compare our region of the Milky Way galaxy, where our solar system is located, to a typical nuclear star cluster, we'll find that a nuclear star cluster has a stellar density that's about 1 million times greater than in our region of the Milky Way galaxy. So, in fact, these are the largest stellar densities that you'll find in the entire universe. So, one obvious question is, how do these things form, and why are they so common? Why is it that almost every galaxy we look at has one of these at its center? Well, there are basically two theories. One says that gas falls into the center of the galaxy, and then stars form in the center of the galaxy out of that gas. Another theory is that you have smaller clusters of stars that form elsewhere in the galaxy, but then they migrate inwards towards the center, and they all merge together to form this very large nuclear star cluster. So, in my research, I helped get a better sense of the answer to this question, and the answer is it's kind of complicated. It's probably a mix of both of these effects. So let me show you a few images that I worked with in my research. So this is the galaxy NGC 300, and we're very zoomed out here. We can see the entire galaxy. You see this tiny little dot at the center of the galaxy? That's the nuclear star cluster. So let's zoom in on that. Now you're seeing an image taken by the Hubble Space Telescope of the nuclear star cluster located at the center of NGC 300. And this is the type of data I worked with in my research at UCI. So I'll leave you with this. Here are a bunch of images of the galaxies that I studied. And then as you go down the columns here, we zoom further and further in. So for example, here's a galaxy where we can see the entire structure. We zoom in further and then even further, and we can get a picture of the nuclear star cluster. So I'll end it here. And that's all we needed to talk about for chapter 33. So in the next video, we'll start chapter 34. Until then, as always, be safe out there, be healthy. See you later.